everyone, it's Olivia here, Olivia's Online Tuition, and today we're going to be going through the June 2022 non-regional paper 1 chemistry for the IGCSE Edexcel. So everything is timestamped in the description if you want to kind of jump around, but let's get started. Question 1, the diagram shows the electronic configuration of an atom of an element. Part A is to name the part of the atom that contains the protons and the neutrons. Well, they are both in here. The nucleus contains the protons and the neutrons. The shells contain the electrons, which are these kind of rings around the outside. Then part B, give the number of protons in this atom, where the number of protons is always equal to the number of electrons, in order to keep the charges balanced in the atom. So therefore, how many electrons does it have? Well, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Therefore, it must be 11 protons as well. And then give the number of the group that contains this element. So the group are the ones that go kind of downwards. So like group 1, group 2, then group 3 being over here, the metals, in the periodic table. So which group has 1 electron in its outer shell? Well, that is group 1. Then give the number of the period that contains this element. Periods are the ones that go across in the periodic table. That would be, so remember the first two were kind of like scattered, there's like one there and one there, and then all the way along there, right? So periods are ones that go across, and that you can figure out by looking at how many shells something has. So the outer shell has 1, and then 2, and then 3. Therefore, it's going to be in period 3. And then give the charge on the ion formed from this atom. So ion, remember, is something that's gained or lost an electron. And this guy is going to lose this electron. And if it loses an electron, it's going to form a positive charge. Because if it's starting at nothing and then losing, taken away, a -1 charge, that's a minus situation. Therefore, we're going to have positive 1. So that's the ion charge it's going to form. And there we are. That is question 1. Question 2, the box shows some changes of states. There they all are. The table lists some physical changes. Complete the table using words from the box to show the change of states for each physical change. So water to ice, if we put that in the freezer, that's going to freeze. So therefore that's freezing. Then steam to water, that's like when you go in a shower and then the water on your window touches your windows and condenses from condensation. That's going to be condensation. Solid wax to liquid wax. Well, it's just going from a solid to a liquid. The fact that it's wax bears no relevance. That's just melting. And then iodine crystals to iodine vapor. Remember, crystals, that's just a solid, right? Like crystals, like salt crystals, right? Going to a vapor. So just trying to make it more complicated than it is. It's just essentially just saying solid to a gas, essentially. And that is going to be sublimation. In part B, a student plans to obtain salt crystals from a mixture of salt and sand. The student adds pure water to the mixture to dissolve the salt. States 2 things the student could do to make the salt dissolve quickly. So say you're trying to, I don't know, make salt dissolve in water. Like, say you're making pasta, or say you're making like a hot chocolate, right? And you're trying to dissolve the hot chocolate powder into your water or your milk, whatever you do to it. So what you're going to do first is you're going to stir it, right? Because otherwise it's going to just kind of sit there. So you need to stir it. That's one thing. Then the next thing you could do is obviously trying to make hot chocolate in cold milk. Doesn't work very well. It all just clumps together. It doesn't stir in very well. All sticks to the spoon. It's a nightmare, right? So what you normally do before you make hot chocolate, you warm the milk up first, at least a little bit. Then you can mix it in a bit better, and then you can heat it the rest of the way, right? Or you might have already heated it all the way, the milk first, then just put your chocolate powder in, and then gone from there. But the moral of that story is you need to heat it up as well. Heat it. That'd be that. And then part 2 states what the student should do next to separate the sand from the salt solution. Well, they could just filter it, couldn't they? Like you're at the beach when you pour the salt water, not the salt water, the sand and the water with like a funnel. Same thing here. Filter it with, in this case, we're going to use something like filter paper, which makes it a bit easier. Can we see that? Yeah, it's a bit cut off, but we can see it with filter paper just to get the sand out. And there we are. That would be the first part of question 2. In part 3, describe how the student can obtain pure dry crystals of salt from the salt solution. So what they've got is a solution, a beaker with some salt water in it. So they want to know how they're going to get that salt back out again. So first thing they need to do is get rid of all that water. Because if the water's gone, salt's going to be left on its own. What they're then going to do is they're going to heat the solution, which will evaporate some of the water. There we are. And then you might have done this practical with like the bright blue copper sulfate crystals, you know, those like bright blue ones. So what you probably would have done is heated it a little bit in your evaporating basin, and then you would have left it overnight. Then you're going to leave it to cool overnight, which is then going to get rid of the rest of the water. And if there's anything left, any water still remaining in that beaker, it'll just be like kind of like run off. Like the crystals will kind of be a bit soggy, and there's kind of like water left at the bottom. Then you can kind of just like pour off that water, filter out the crystals, just leave this. Pour the water away, right? And the last thing you're going to do is just pat it dry with a paper towel. Then you'll have your results. And yeah, that would be 4 marks for these 4 points. On we go. Question 3. Crude oil is an important source of organic compounds. The diagram shows how crude oil can be separated into fractions by fractional distillation. States what happens to the crude oil when it is in X. X is this furnace here. So therefore, what the furnaces tend to do, they tend to heat things up. Therefore, we're gonna, it is heated. Okay, and then part 2, give the name of fraction E, or fraction E is this one here. So what are they all? That's the main thing. So F, it depends on which country you're in. Sometimes they're called slightly different things. So F is normally called either the refinery gases, or you could sometimes call them refinery gases, I suppose. That's what I tend to call them. That's refinery gases. And then E is petrol, or you might call gasoline if you're that way inclined, if you're more Americanized. And then D is, what is that? That is kerosene. And then C, that is diesel. To brainstorm, remember. B, that is heavy fuel oil. That's not how you spell heavy, is it? Heavy fuel oil. And A is bitumen. And there we are. So what are they all used for? Well, refinery gases, that stuff you get like in your boiler, on your gas stove, in aerosols, that sort of stuff. Petrol and gasoline is used for the obvious cars, you know. Kerosene is plain fuel. Diesel tends to be bigger car fuel, like trucks, lorries, 4x4s, vans, that sort of stuff. Heavy fuel oil, that's things like boat fuel, power station fuel, that sort of stuff. And then bitumen is for roads. So fraction E is gasoline or petrol, whatever one you fancy calling it. And then fraction A use is roads. That's what bitumen is used for, either roads or things like roofing. Either or. There we are. Part B, one of the compounds in fraction D is tridecane, which can be cracked to form shorter chain hydrocarbons. State the catalyst and temperature used in this cracking reaction. So catalyst, you can have a couple of options here, and normally people tend to go with silica. I think it's the easiest one to remember. Or you tend to have alumina or zeolite. So I learned it as in school, and that's kind of like the brand name for it, but zeolite would also work. And the temperature, anywhere between like 600, 700 degrees. Let's go 650, spice it up today. There we are, 650 degrees, that'd be that. Then the equation shows an example of a catalytic cracking reaction. There it is. Give 2 reasons why this reaction is important. So why do we crack compounds? So one of the reasons is that shorter chain hydrocarbons are considerably more useful. If we go back to our kind of fractional notation column up here, all of these, particularly refinery gases, used in every home pretty much, up at, like in the world pretty much. If you have any sort of aerosol, any deodorant that's in a gas form, if you have a gas boiler, if you have a gas cooking hob, it'll be used in all those places. If you have a caravan or kind of like a mobile home, then they'll use refinery gases. Petrol is very important, you know, for obvious reasons. Kerosene, you know, planes are important, I guess. Much more important than bitumen, which is one material used to make roads, where there's several others. So what they do then with cracking is they crack in order to get more profitable hydrocarbons, ones that are more useful to the everyday consumer. So give 2 reasons why this reaction is important. So the main reason, the ones I just mentioned, is that shorter chain alkanes are just more useful, more in demand, or anything of that description, or you could put here, are more useful. And then the other thing as well is that this guy and this guy, which you may have noticed are not alkanes, but these guys are not, these are alkenes. This is the one way that you can really get alkenes on the GCSE syllabus. So alkenes are also pretty useful. And then what do alkenes do? Why are they more useful? So more useful, because otherwise we're just saying the same thing twice, aren't we? So more useful as they make polymers. If you do not condensation, polymerization, that's the other one. Addition polymerization, you know, when you open up double bonds, like if I draw it down here, where you have this as your alkene, and then you open it up and you get this. And there we are. So this would be ethene and this would be polyethene, you know. So that's used all over the place. I mean, plastics everywhere, aren't they? That means also useful to make polymers. Oopsies, you can't even see my little diagram. There we are. That's what I was showing. Ethene going to polyethene. There it is. In part C, sulfur is an impurity in crude oil. Explain why this is the problem for the environment. So what happens when sulfur is kind of infiltrating crude oil? So what happens is it will then combust like the fuel does in an engine, because engines are rather hot, right? So the sulfur is going to combust with oxygen and make sulfur dioxide. So let's put that down. And then this sulfur dioxide, what that does is it then dissolves into rainwater, because it's dissolvable, it's soluble in water. So it will dissolve in the rainwater and then it will turn into sulfuric acid. No good. Imagine that being poured down in rain. Obviously dilute version, but it'll still affect things like calcium based and things like limestone and the like, so like buildings, bricks, statues, that sort of stuff. So then it dissolves into rainwater and produces acid rain, is what we call that. And there we are. And that would be the end of question 3. Question 4. A student uses the reaction between iron and oxygen to find the percentage of oxygen in air. The diagram shows the apparatus the student uses. Part A states why the iron powder needs to be wet. So iron reacts with oxygen very rarely, because remember, iron isn't so reactive, so it doesn't really do very much. But what it does do is rust. What do you need for rust? You need water. So water is needed for iron to rust, and that rusting reaction is what's going to use up the oxygen. So it won't really be able to do it on its own, because it's just not reactive enough for that. In part 2, state the colour of the compound formed in the reaction between iron and oxygen. Well, what colour's rust, right? Rust is kind of like a browny, orangey colour. So let's go with brown, that'd do. And then give it the formula of the compound form. Well, that's just knowing the formula of rust. And rust looks like this. Just something to learn. Rust is iron oxide, which looks a bit like that. And then explain the advantage of using iron powder rather than pieces of iron. So the advantage is that the reaction is going to occur a lot faster, because you have a much better surface area to volume ratio. It means the reaction is going to happen a lot faster, which means you're not going to be waiting there all day dilly-dallying, waiting for the reaction to occur. Let's put it down. So powders have a greater base surface area to volume ratio. Let me move it downwards. So the reaction will occur faster. There we are, that'd be 2 marks. In part B, the syringe in the diagram shows the reading at the end of the experiment. Complete table 1, show the readings on the syringe, give both values which is the nearest 1 centimetre cubed. So I made the picture of the syringe really quite large here. I think it has to be, because these lines they've been a bit harsh here. So there's how many? 1, 2, 3, 4, 5, 6 lines, I would say. Therefore, the reading at the ends is 16. That's what we know, because we've been told that this reading, this syringe here, this picture is at the end of the experiment. So then, what is 16 greater than 65? Let's have a look. 65, I should just do it in my head, but I can't be bothered. 81. And there we are, that'd be 2 marks. Then part C, the student repeats the experiment to obtain a different set of results. There they are. Table 2 shows these results. Use the results from table 2 to calculate the percentage by volume of oxygen in the air. Okay, so this percentage by volume of oxygen in the air, that's going to mean like the volume of oxygen out of like the total volume, that I find like the fraction by volume of oxygen in the air, almost, and then times it by 100 to get a percentage. We need the volume of oxygen and the volume in total. Well, let's have a look. So the volume of oxygen, well, we can just take these two away, can't we? And get the syringe at the start, syringe at the end, because it's going to have eaten up all the oxygen and pulled it outwards. Therefore, 90 minus 22, well, that is Then we have 68, the volume of oxygen, and the volume in total. So we've got the volume of air in the conical flask and in the gas tube. And then we have, which is this bit here. I also often see students confused because they think glass tube. Well, this is technically a glass tube, which it is, but they don't mean that, right? Because the answer here for the volume in total is not just 260, because that's just the volume of air in this section here and in this section. But you also have your starting amount of air in this syringe. No good, right? So you've got to also add that on. So therefore, you're going to have 260 plus 90, which is what, 350. And then divide those, times it by 100, and you get 19.4%. And there we are. And that is the end of question 4. Question 5. This question is about alkanes and alkenes. The alkane C5H12 has 3 isomers. Say what is meant by the term isomers. So people always mix this up with isotopes. Maybe sometimes ions as well, but because those 3 terms sound very similar, right? Isomers, isotopes, and ions sound very similar. So the isomers, that's ones that have the same molecular formula, but a different structural formula, which is very different to isotopes, which have the same number of protons but a different number of neutrons, and also different to ions, which have a different number of electrons, either added or also taken away some electrons. So yeah, 3 terms, very similar, very important that you know the difference. They do ask about them all the time. And then calculate the relative formula mass, MR, of C5H12. So if you look at a periodic table and figure, okay, what is the MR of carbon and what is the MR of hydrogen? So let's flip back to the periodic table, let's have a little look. Here it is. You always get one of these, so it's always at the kind of the second page on your exam. So we're looking for carbon, we're looking for hydrogen, if we recall. Well, carbon is here, but which number do you pick? So for MR, you're always looking at the top number. So carbon is 12, and hydrogen, which one here, is 1. And let's go back. And there we are. So now we know that we have 5 carbons, so that's 5 times 12, added on another 12 because there's 12 lots of 1. And that gives us, and there we are, that's that. Then this is the displayed formula of one of those isomers. Give the name of this isomer as a carbon, or as an alkane, I should say, with 1, 2, 3, 4, 5 carbons. Means that this is pentane. Like a pentagon is a shape with 5 sides. Pentane is an alkane with 5 carbons. And there we are, on we go. Then part 4, draw the displayed formulae of the other 2 isomers. So be careful with this because you can't have anything that's accidentally the same thing. So you can't like bump one of these carbons like up here and like replace this hydrogen with this carbon there, because that would technically be the same thing, because we're counting for isomers how many carbons we have in a row, right? So if we still have 5 in a row in any which way, like in like where you can't like double back on yourself, then it's still the same isomer, still the same version. But if you kind of move a carbon somewhere else, so say you put one on the middle, for example, like this, then you now only have like 4 in a row, if that makes sense, because you've got 1, 2, 3, 4, 5, because then you've got one up here, but then you can't really count this one without going like around a corner, if that makes sense. So this is a different isomer. If I put this carbon here, then it no longer will be, because we've still got 5 in a row, therefore it's still just pentane. So then if we fill in all our hydrogens, remembering that every carbon has to have 4 bonds, then kind of you can check that you've got everything. If everything has 4. So that's that one. And then what else could we do? So again, we can't just move one of these down here, because then that would still be the same, like 4 in a row. So what else could we do? We could move this to be also on the middle one. So we could have a carbon here with all the carbons around it, if that makes sense. That would also work. So if we draw the hydrogens, and there we are. So this one, again, doesn't have the same number in a row. This one has 3 in a row here, kind of whichever way you look at it. Down and across. This one has 4, this one has 5. That's what you're looking for with isomers, having a different number in a row. And there we are, that's that. Part B, ethane and ethene both react with bromine. Describe the differences in the reactions of ethane and ethene with bromine. So what I'm going to do first is draw those 2 out. I won't draw that out in the exam, like in the answer space. I put it in a separate place, so I'm just going to put it in the answer space, but I don't have it really right anywhere else. So I'm going to draw them out. Okay, and there it is. Remember, don't draw this in your answer space in the actual exam because obviously you just run out of space. But I don't have anyone else, so I'm just going to put it here. I'm going to delete it in a second. So these are my two reactions. So what do I form with each of them? Remembering that bromine, Br, is a diatomic molecule, therefore there's always two parts to it. So what am I going to get here? Well, in this case, if we remember that with alkanes, what happens is the process of substitution. That's what happens. A substitution occurs, which requires lots of energy because alkanes aren't very reactive because they don't have any bonds to break to form kind of new bonds, if that makes sense. Like this double bond here can break and form an extra two bonds here and here, but this one can't do that. Therefore, it needs ultraviolet light in order to do it. And this is a substitution reaction. Put that there so we remember to write it. And then what happens then, we're substituting one of these for one of these, right? So we're going to get this. Doesn't matter which hydrogen you swap out for bromine, could be any of them. As long as it's one of them, that's fine. So then you get this, you get hydrogen bromide, which is this guy, and you get this guy here, which is bromoethane. And then with this one's got more energy, so you don't need to do anything with really any energy. You don't need ultraviolet light, you don't need any catalyst or anything, you'll just do it on its own. And this is an addition reaction, slightly different. The double bond fully opens and both of these bromines will just hop in, right? So therefore we're going to get this, where the four hydrogens already had just kind of tuck up here and down here. Then you get a bromine and you get a bromine. And this is dibromoethane. This is bromoethane, this is dibromoethane because there's two of them. Di in chemistry is a prefix of two. There we are. So let's write all that down and I'll read it out to you in a second. And there we go. And that would get you 5 marks. I've just kind of shrunk this, we can put it all in. So ethane reacts with bromine through substitution reaction, whereas ethene undergoes an addition reaction. That would be 2 marks there. Then ethane needs ultraviolet light in order to react with bromine. Ethene does not, that'd be another mark. Then ethane produces dibromoethane, hydrogen bromide, whereas ethene produces dibromoethane only. And that would be technically another 2 marks. They could kind of, or even not say this one and still get 5 with just this point and this point. But yeah, I think this tells a nice full story. There we go, that'd be 5 marks. On we go. Question 6. A student uses this apparatus to investigate the reaction between magnesium and dilutes hydrochloric acid, another kind of gas syringe situation. The word equation for the reaction is magnesium plus hydrochloric acid. It goes magnesium chloride plus hydrogen. Completes the chemical equation for this reaction. So remembering the magnesium is in group 2, means it's going to form 2 plus ions, and then chloride in group 7 means it forms minus 1 ion. So then balancing these, we need 2 chlorides per magnesium ion, therefore we're going to have MgCl2. And then hydrogen is diatomic, which means that we need 2 of them. And there we are, that's that. And then give it the test for hydrogen. Well, hydrogen burns with a squeaky pop. So there's a squeaky pop with a lit splint. There we are. And then part 3, the student uses 0.09 grams of magnesium and 0.025 moles of hydrochloric acid. Show by calculation that hydrochloric acid is in excess. Okay, so we want to work with moles. There's no point in working with 2 different units, grams and moles. That's just a recipe for disaster. So let's convert this grams into moles. We might as well. So what is the equation for that? Well, we have mass is equal to Mr. Mole. And that's that one. So then we have mass, which is 0.09. Mr. is the top number on the periodic table, which I know for magnesium is 24, times by the number of moles, which means that then I'm going to divide this down there. So the number of moles is equal to 0.09 divided by 24, which is 3.75 times 10 to the power of minus 3. Standard form is fine on a chemistry paper. Is that what it calculator gives you? That's what it gives you. Okay, so now we have, I'm going to put it over here, run out of space at the bottom. So now we know that magnesium has 3.75 times 10 to the power of minus 3 moles. And we know that HCl has 0.025 moles. Then how much do we need of each? So if we look at this symbol equation, we do need double the amount of H. So yeah, let's see. So say if we look at magnesium, so magnesium we have this, and then 2 lots of magnesium would be that 3 times 2. which is 7.5 by 10 to the power of minus 3. So if we convert this, is 0.123 0.075. Is indeed, there we are. So this is how many moles of HCl we actually need, because we need double the amount that we have for magnesium, and magnesium we have this much, therefore we need double that much, we need this. However, we have loads more than that, right? We have 0.025 moles, loads and loads and loads more. Therefore, what we need to say is that, so if I shuffle this down slightly, we could say we need 0.0075 moles of HCl to react with 3.75 times 10 to the power of minus 3 moles of magnesium, but we have 0.025 moles, which is greater. And there we are. And that is that, 2 marks. Then part B is everyone's favourite question, the drawing the graph question. Everyone loves this question. So the student measures the volume of hydrogen collected at regular intervals until the reaction stops. The table shows the student's results. There they all are. Plot the results. Easy peasy. 0, 0, that's that one. And then 15, which is, well, if that's 20, half of that will be 10. Therefore, halfway between 10 and 20 is 15. So about here, up to 40, which is there. And then we have 30 and 68. Well, 30 is going to be halfway between 20 and 40, all the way up to 60. Well, that's going to be 70. That's halfway between 60 and 80. Therefore, 68 is going to be one before that, which is there. And then we have, what do we have then? 45, which will be halfway between 40 and 50. And 80, which is... Eyesight's too poor for this. There we are. That's about there. And 60 and 88, that's 60, that's 90, so 88 will be there. And then 75, which is 60, 80, that'd be 70, 75 will be here, up to 88, which is there. Is that right? That's 60, 70... Oh, 75, not 65. What am I doing? 75 here, all the way over there. Looked wrong, which is quite nice. Quite nice because you can see that one looked too close together. You can kind of tell when you're making errors with these graph questions. Then all you need to do is connect them up, which is kind of easier said than done on this system. So I'm going to use a straight line there just to make life a bit easier, and then a straight line here as well to make that a bit easier. And then obviously in your exam, don't do that, don't use your ruler, but this could be a bit of a mess otherwise. Yeah, I think that's all right. There we are, that's that. Draw a line across it, that's that one. Then determine the volume of hydrogen collected in the first 10 seconds. Well, where's that? So 10 seconds, that's here. So then going up to there and across. That's about there. Oopsie daisy, kind of halfway through that box, which is 22, 24, about 25 centimeters cubed. And there we are. That is all of part B. In part 4, explain why the rate of reaction is greatest at the start of the reaction. So, because at the start of the reaction, you have all your stuff, don't you? You have loads of stuff that you can react. There's an abundance of particles of both types, magnesium, hydrochloric acid, there's loads of stuff in there, right? Whereas near the end, you run out of stuff. Therefore, there'll be less to react. So at the start, there is a greater concentration of reactants, which means there's going to be more collisions, which means there'll be more collisions per unit time. You'd have to say there's going to be more frequent collisions, which also has a time element, or more collisions per unit time. You have to have some reference to time in there. Either can you say the word frequent or can you say per unit time. So which increases the number of collisions per unit time. There we go, that'd be 2 marks. Okay, this is part C from the other page. I kind of popped it down here into my face scan so we can draw it on the graph. So the student repeats the experiment at a temperature 5 degrees higher than the original temperature. All other conditions are kept the same. On the grid, draw the curve you would expect the student to obtain. Okay, so What's going to happen? Well, it's going to be at a faster rate because there's a high temperature, means that the rate's going to be faster, which means that this curve is going to be steeper, but it's still going to end at the same spot. Condition, it's still going to run out of stuff at the same time, or roughly the same kind of points, right? It's going to happen quicker, so it's going to be faster, it's going to run out of stuff quicker, but it's not going to suddenly make more stuff, right? So we're going to run out of stuff at the same points, right? So it runs out of stuff at about kind of 88, right? So it's still going to run out of stuff there, so I'm going to kind of keep that consistent, put it about there, but I know that it's going to go a bit faster, so kind of something like that, which my curve is a bit high, but you kind of get the picture. So something like that, where this line here should be running at the same place as where the purple one is, which is easier said than done. Something like that. So it's a bit steeper. This should be a bit smoother in theory, but this is the hard to draw on here. But with a pencil, a bit easier. And then finishing off at the same place, it'll just finish at that point sooner in time. And there we are. That's part C. Part 2, explain in terms of the particle collision theory how increase in temperature affects the rate of the reaction. So first things first, I'm going to tell you how it's going to affect the rate because that's what it's asked me for. So let's put that down first. So increase in temperature will increase the rate. And then why? That's the main thing. So if the particles are moving faster, they're going to have more kinetic energy, meaning they're going to collide more. They're also going to have more energy, which means that more of them are going to meet the activation energy requirements. So that's the amount of energy that they need in order to have a successful collision, right? Because that's two things that have to go right in order for them to react. They have to first hit each other and have enough energy. So increasing temperature helps with both of those things. Let's put that down. There we go, that's what I would say then. So increasing the temperature will increase the rate of reaction, I should have said. And then the particles have greater kinetic energy, so move faster and collide more frequently. Then more particles have energy greater than the activation energy, so more collisions occur per unit time. There we go, that's the end of question 6. Question 7, this question is about copper and copper compounds. A sample of copper contains 2 isotopes, copper 63, relative abundance of 69.5%, copper 65, relative abundance 30.5%. So what is meant by the term isotopes? We've been through this earlier, looking at isomers versus isotopes. So isomers, different molecular, same molecular formula, different structural formula, and then isotopes, different number of neutrons but the same number of protons. So this is the formal definition for it. So it's a different version. So a different version of the same elements with the same number of protons but a different number of neutrons. There we are, that'd be 2 marks. And then part 2 is a calculation. So calculate the relative atomic mass, AR, of this sample of copper. So the equation for this is, so you find your AR, you take the mass number of your first isotope and times it by the abundance of that first isotope. Then you add that to the mass of the second times the abundance of the second. And you kind of keep going for how many isotopes we have. We only have 2, therefore we're going to do it twice, but we would add N3 times A3 if there was a third one. And then you just divide it by 100. So what we're going to then get is AR is the mass one, which is 63, times the abundance one, which is 69.5. And then we're going to add that to the mass of the second, which is 65, times the abundance of the second, which is 30.5. Then we're going to divide all that by 100. And what do we get? We get 63.6. And there we go, that's 3 marks. Part B, when copper 2 carbonate is heated, copper 2 oxide and carbon dioxide are formed. What is the name of this type of reaction? So a lot of people will automatically go oxidation reduction, but remember, if it's like a full reaction, then if it's going to do one of them, then chances are it's also going to do another, unless it's reacting with oxygen. In that case, it'd be oxidation. So it's not going to be either of these two, because it's not reacting with oxygen, so it's not going to be any of those two. And then it can't be neutralization, because neutralization is acid plus base, and there isn't a plus anything, right? It's just copper carbonate forming something else. And another thing is heated. You might have called it thermal decomposition in school. They've got chopped off the word thermal, I think because they gave you too much of a clue, but it's thermal decomposition, or just decomposition, because it's kind of decomposing into 2 products, starting from like the first one, you're kind of splitting. And there we are. And then which colour change occurs during this reaction? Okay, so copper oxide, that's like a black substance that forms over like a layer over the copper. So it's going to go to black. So they're going to be blue to black or green to black. And we know it can't really be blue to black because we know that blue with copper is copper sulfate. And we don't have that. We have copper carbonate, so it's not going to be blue. So therefore, it's got to be green. And there we are. That's a tricky colour change. Remember, that one is tough. If you didn't get that one, that is kind of fair enough, I think. But there we are. Let us see. Okay, and then part C is a bunch of kind of mathsy stuff, but we have to kind of get through the writing first. So a student uses this apparatus to find the value of X in the formula copper sulfate X water. Essentially, like X essentially just means that it's kind of in there. So imagine copper sulfate. That's like that's an ionic compound, right? So it looks a bit like this with their big kind of lattice structure. Does that make sense? So what happens with the X water is that water can sometimes kind of fit, if you kind of imagine it, behind these atoms here, like inside the molecule. So we're kind of figuring out with this how many waters are fitting inside this molecule they have to kind of get rid of, which is why salt's going to look a bit fluffy because water is inside the crystals we have to get rid of. And there we are. So this is the student's method. They found the mass of an empty boiling tube, this one here, added hydrated copper 2 sulfate to the tube and recorded the new mass. They've heated it up and they've evaporated it off. They've turned this white and then they've allowed it to cool and remeasured the mass. Look at how much water has left. Okay, on we go. Okay, so the table shows the students' results. Here they all are. Calculate the mass of copper sulfate formed. Well, they've done the mass of the empty tube and the mass of copper tube and copper sulfate. Therefore, we're going to take that away from each other, aren't they? So then we have 28.2. Take away 20.52. I'm not going to do that in my head. You know me at this point. 28.2. Take away 20.52. And that is 7.68. And then calculate the mass of water formed. Well, we have mass of tube and copper sulfate with water, and we have mass of tube and copper sulfate. Therefore, we take away this from this. We take away that, and we get left with this. So therefore, we're going to do 28.2. Take away 31.77. Oh, other way around. Look, what am I doing? Other way around, obviously. 31.77, take away 28.2, and we get 3.57. Okay, and then part 3, show that the value of X is approximately 4. So what have they given us? MR of copper sulfate, MR of water. And we have a bunch of masses. Let's do some mole stuff. Might as well, hadn't we? We've got mass is Mr. Mole, our beloved equation that we use all the time, which we know and love. We've seen it many times now. Mass is Mr. Mole. So let's do mass. Well, we have the mass of copper sulfate. So let's do that first. Might as well. 7.68. We go to the MR of copper sulfate, which is this, times the number of moles. So to find moles, we divide that down there. So moles is equal to 7.68 divided by 159.5. And we get 0.0482. Let's go with that. Let's do the same thing for the water. So we have mass Mr. Mole, we have the mass, which is 3.57, is equal to the MR, which is 18 times a mole. So we divide by 18. Get the number of moles as being 0.198. Okie dokie, I guess approximately 4. Well, let's have a look. So let's figure out how many. So if we have one like copper sulfate, which kind of what they're saying is copper sulfate here, copper sulfate. And then they told us before, where's it gone? Lost it. Is it even on here? Here it is, yeah, here. So it's kind of a 1 mole of this and X amount of this, right? Okay, if this is 1, how much of this do we then have? Let's divide them. So that's water, H2O. If we do 0.198 divided by 0.048, how many kind of lots of this we have greater than the water? Or greater than the copper sulfate, I should say. So if we divide that by 0.0482, we get, would you look at that, 4.11, which is approximately equal to 4. And there we go, that's that. And then part 4, the actual value of X is 5. Give a reason why the calculated value of X is lower than the actual value. Well, if these masses are off, it's going to be off, right? So what they could have done is not fully evaporated the water. If some's still in here, then our copper sulfate mass is too big and our water mass is too small. So therefore, they may not. Yeah, so they may not have fully evaporated the water, so they haven't gotten rid of all the water. But there we are. That will be the end of question 7. Question 8. Diamond and graphite have giant covalent structures made of carbon atoms. The diagram shows their structures. There they are. Discuss the differences between diamond and graphite. Show the structure and bonding, electrical conductivity, and hardness in your answer. So I'm going to lay it out like kind of like a list. That's what I'm going to do. In exam, I'd make it slightly more comparative than what I'm going to make it here, but I'm going to kind of just write it as I'm kind of explaining it for now, and then I'll rewrite it how I would write it in exam, so you can kind of see that out here. I'm not going to be able to spitball a full paragraph out of my head. You have to gather your thoughts first, as you will often do in exams, right? And kind of a little list of all the things you know about these things might help before you start kind of on your endeavour of writing a full 6-mark paragraph. So, what do we know about the structure and bonding in diamond and graphite? So let's start there. So with diamond is a giant lattice. That's one thing we know about its structure. So giant lattice. And graphite is not a lattice because it has layers. Well, still kind of a lattice, but layers are the main thing in graphite that are very different to diamond. Diamond doesn't have any layers, graphite has a bunch of them. That's structure. Bonding, well, they're both covalent bonds. That we do know. So diamond is fully covalent. That's only covalent bonds. They're the only things that are relevant. That's why diamond is the strongest material on Earth. Fully covalent bonds, and they are really strong. However, graphite does have covalent bonds. That can be said. So all the kind of black lines you're seeing on here, they are covalent bonds. However, graphite also has intermolecular forces. And those work between the layers. So between the layers, which why the layers can slide over each other, like pencils. If you write with a pencil, it'll just kind of rub off a layer on the paper, because they're really weak in the forces. So the friction between your force of applying the pencil on the paper and the friction between the pencil and the paper, that's enough to kind of obliterate those individual forces and just slide it off straight onto the paper. So that's that. Electrical conductivity. So diamonds cannot conduct. So let's put that. Let's just put no conduct, I guess. No conduct. And graphite can. Let's put yes conduct. I guess. And why? So with diamond, you might be able to see on here, if you look at kind of this one atom right there, then diamond forms 1, 2, 3, 4 bonds, as most carbon-based things do. However, graphite, look at an atom of graphite, like here, it forms 1, 2, 3 bonds. Difference, right? So in diamonds, each carbon forms 4 bonds. If you remember, carbon is in group 4, therefore it has 4 electrons at a shell, hence why it forms 4 bonds normally. So you'd have 1, 2, 3, 4 dots from the kind of central carbon, and then these kind of other carbons around the outside, let's see that, yep, would all also kind of share an electron to form a really strong bond. Then each of these carbons would form another kind of 3 bonds with other carbons. Then that structure just continues to grow until it ends, right? Until naturally it bonds with itself or comes to a close, right? Something else in the way, like a rock or something. So that is that. With graphite, however, graphite only forms 3 bonds because the layers haven't been pushed together enough to get this atom close enough to this atom in order to form a bond between them. It just, like a covalent bond between them, because it just isn't close enough together. If it was under more pressure, different story, but it's not under enough pressure, therefore it's only going to form 3 bonds. So it's going to form 1 here, 1 here, and 1 here, with each of these 3 carbons. So very similar bonding. It's just that this central then carbon atom has 1 electron floating around, and each carbon will each have 1 what we call delocalized electron, which you have to call it that. They don't like anything else. No free electrons, they don't like that anymore. It has to be delocalized electrons, which can hop from carbon atom to carbon atom, carrying the flow of charge. So that's why. So we're going to put that down in a second. So I've just put no conduct and yes conduct for now, but you have to kind of explain this to them in your paragraph. And then hardness, well, diamond is harder than graphite. Diamond is the hardest and strongest material on Earth. So diamond is harder and graphite is softer. And it kind of has to be, because I mean, just the slight pressure of me kind of rubbing my pencil on my hands will be enough to like turn it slightly grey. We can see it there, right? This is slight, I'm not kind of pressing really hard or anything. Even that slight pressure is enough to break these bonds. It's very soft, right? So there we are. So what I'm going to do then is I'm going to write all that out and then talk you through it in a second. I put a big long paragraph. Obviously I've run out of space, but I write quite big. So you shouldn't run out of space in yours, hopefully. So in diamond, each carbon atom bonds with 4 other carbon atoms, whereas in graphite, each carbon bonds with 3 other carbons, with 1 electron being delocalized. And then graphite can conduct electricity as its delocalized electron can carry charge to the structure. Diamond has no delocalized electrons, so cannot conduct electricity. And then diamond is hard as it's made up of very strong covalent bonds, which require a lot of energy to break. Graphite is soft as it has weak forces between the layers. I think I misspoke earlier. I can't watch back the video. I think I said intermolecular forces, which it does not have. I misspoke. It's because those are just between molecules, and obviously this is a massive structure with lots of atoms, therefore not a molecule. It does have just forces, so you can just call them forces. GCSE technically they do have a name, they're called van der Waals forces, after Van der Waal, who created them, but that's A-level chemistry. Don't you think about that, or international baccalaureate chemistry if you do the IB. But that's that, so sorry to misspeak earlier, but that would be 6 marks, and there we are, happy days, moving on. In part B, C60 fullerene is a simple molecular substance made of 60 carbon atoms. The diagram shows its structure, there it is, like a ball. The table shows the approximate melting points of diamonds, graphite, and C60 fullerene. Okie dokie then. So, explain why C60 fullerene has a much lower melting point than diamond. Right, so it's still made up of these covalent bonds, which are, in fairness, very strong. But the main phrase here is simple molecular substance. So this guy is a molecule. Big one, be it that, it's got 60 carbon atoms in it, so quite a big one, but a molecule all the same. Therefore, this guy is going to have intermolecular forces, and those, we know, are rubbish. So that's why it has such a low melting point, because essentially the thing holding this in a ball shape, imagine the only thing that's keeping this from not just kind of flowing all over the place are kind of these forces kind of between these guys going kind of this way. Those between them as well, sure, but the ones kind of holding the football out, like the gas, kind of like the, in a football you have like the gas pressure in the middle that makes it a ball, right? In here you just have these intermolecular forces. So without those, crush, right? Rubbish. So let me write all that out and then I'll kind of go through it again in a second. And here we go, this will be 4 marks, 2 per paragraph essentially. So C60 has weak intermolecular forces between the molecules which require little energy to overcome. One for saying intermolecular forces, saying that they're weak, and the one for saying that they require little energy to overcome. And then diamond and graphite have many strong covalent bonds. This also has covalent bonds, but it's only got 6 of them, whereas diamond and graphite kind of go on forever, seemingly, right? Or can do anyway. Graphite have many strong covalent bonds which require a lot of energy to break. There, that will be the end of question 8. On we go. Question 9. This question is about the oxides of lead. Yellow lead oxide can be reacted with hydrogen to produce lead. Complete the equation for the reaction by adding the missing state symbols. Okie dokie then. So we've got lead oxide, which is a solid, plus hydrogen, which we all should know is a gas, going to lead, which is a metal, so therefore it's going to be a solid, plus water, H2O, either steam, water, or ice. Well, if we think about the kind of situation that's going to be arising here, we can probably assume that it's going to be just water, therefore a liquid. I only thought to hesitate because it could technically also be a gas. I mean, it depends if they're heating this up or not, but they haven't really told us whether they're heating it or not, because obviously we don't know the reactivity of lead oxide because we are but a GCSE student, or an IGCSE student in this case, so we're not to know, right? So either liquid or gas here would have sufficed to check the mark scheme, because we aren't to know whether we're heating it up or not, therefore liquid or gas would suffice for this one. And then what is the charge on the lead ion in PbO, lead oxide? So we know that oxygen's in group 6, therefore it's going to have a 2- charge, and there's no little letters here which represents having to like double or triple a charge to make it balanced. Therefore Pb, or lead, also has to have a 2 charge, therefore it's going to be 2+. Has to be opposite to this one because lead's metals, I should say, are always positive charges, always, every time. either going to be +1 or -1, or +1, sorry, or +2. However, it's -2 here. Let's go with +2 here. If it was -1, then it'd be -1 as well. This matches. And then explain why the reaction of yellow lead oxide with hydrogen is a redox reaction. Okay, then redox is reduction and oxidation happening at the same time. So if we think about what's happening here, then I mean lead is losing oxygen, so we know that's being reduced, and the hydrogen is gaining oxygen, therefore it has been oxidized. So let's write that out. And there we are. So lead oxide loses oxygen, so it's reduced, and hydrogen gains oxygen, so it's oxidized. And this is kind of just like one version of a redox reaction. The other one is that like the oil rig, which you might have learnt. Oxidation is loss of electrons, reduction is gain of electrons. But unless we kind of split this up into half equations, we're going to see what's happening with the electrons. So we're going to look at the oxygen. Obviously, if oxygen is not involved, it's going to be the electron stuff. We can see oxygen's happening, moving around here, which means that we're going to look at that. And there we are. And then part 5, part 4, I should say, we can see that, yep. Describe a physical test so the water produced in this reaction is pure. So we know that pure water, or we should know anyway, that pure water boils at 100 degrees exactly. If it does not boil at 100 degrees exactly, then it is not pure. So that's what we're going to do. So we are going to measure the boiling point of the water, and then if it is not 100 degrees Celsius, then it is not pure. But yeah, that would be 2 marks. Omega. Part B, when red lead oxide is heated, yellow lead oxide forms. The equation for the reaction is this here. A scientist heats a known mass of red lead oxide in a crucible in a fume cupboard. The scientist leaves the crucible to cool, then records the total mass of the crucible and its contents. Describe what the scientist should do next to make sure that all the red lead oxide has reacted. Part B, when red lead oxide is heated, yellow lead oxide forms. The equation for the reaction is this here. A scientist heats a known mass of red lead oxide in a crucible in a fume cupboard. The scientist leaves the crucible to cool, then it records the total mass of the crucible and its contents. Describe what the scientist should do next to make sure all of the red lead oxide has reacted. Okay, the longer they're heating it up, the more oxygen's coming off until eventually nothing's going to change. So what they could do is just keep heating it up until they notice that no mass is changing, right? So they keep weighing it, they keep finding the total mass that's gone, essentially. As soon as that stops changing, then that must mean that all this is converted to this, because there's none of this that's left to be made. So there must be no more of this left. Does that make sense? So they would keep heating the lead oxide, or red lead oxide, and measure the total mass, and then stop heating when the mass stops changing. So you want to kind of repeat, like, heat it, cool it, weigh it. Heat it, cool it, weigh it. Heat it, cool it, weigh it until the weight does not change. The mass doesn't change. Because when the mass stops changing, then that must mean all this is gone, because no more is converting to oxygen, which is then going to leave, right? And that's that. On we go. In part 2, the red lead oxide used in the reaction has a mass of 5.48 grams. Calculate the maximum mass of yellow lead oxide that could form. We've been given our MRs, and I've just kind of plopped the equation from above here, because I'm assuming we're going to need it. So we've been given a mass, we've been given MRs. So, for the third time this paper, bit of a jumble, we're going to use the same equation. As the more chemistry papers you do, the more you realise they're not very creative with their maths questions. They're always the same. It's always mass Mr. Mole. That's the kind of main equation. If you're going to learn any chemistry equation, learn that one. That one comes up all the time. It comes up 3 times in 3 separate questions in this one paper, right? It comes up all the time. So, mass, we know that's 5.48. That's the mass of red lead oxide, which is this one here, is the MR, which is 685 times by the number of moles. And then moles is equal to 5.48 divided by 685. And that is 8 times 10 to the power minus 3. Okie dokie. And then I'm going to reread it again because I didn't even pay attention to what I was reading because it's always going to be the same. You're going to do this first. The maximum mass of yellow lead oxide that can form. Okay. That's how many moles of this that we have. Therefore, how many moles of this are we going to have using our molar ratio? So we have a molar ratio currently of red lead oxide to normal lead oxide, or I guess yellow lead oxide, that's Q, no, there we are, is 2 to 6. Doesn't matter what you call it, you could call it red lead oxide and yellow lead, it doesn't matter, right? I just made this up. So 2 to 6. 2 to 6, numbers in front. Then I'm going to simplify this because I might as well to make it 1 to 3, just half both the numbers. And then I know that this one, the red one, is 8 by 10 to the power of minus 3. Means that this one, this is times, if I times that by 8 by 10 to the minus 3, that'll get me from 1 to that. Then we're going to do the same thing here, because that's times 3, therefore this is times 3, right? So that times 3 is 0.024. Okie dokie. So then my moles of PbO 0.024, and then I want a mass. I'm going to do the same equation again for the 4th time. Mass is equal to the MR, which we've been told is 223, number of moles, which is 0.024, times those together, and we get 5.352 or 5.35, I think that'll do. And there we are. And that is the end of question 9. So yeah, don't be daunted by these questions. They're literally always the same. Don't worry about them. Just write as mass Mr. Mole, find your moles, deal with the ratio stuff, classic maths ratio problem, and then go from there. Anyway, on to the last question, question 10. I think it's the last question. I guess we'll see. See you then. Question 10, which is the last question to confirm. This question is about ammonia and ammonium compounds. Excellent, I love ammonia. So ammonia, NH3, is a simple covalent molecule. Draw a dot and cross diagram to show the bonding in a molecule of ammonia. Okay, so ammonia, we've been told is simple, covalent, somewhere, there it is. We're just going to be dot and cross, which I've kind of told us here as well. So we know that nitrogen is in group 5. If we don't know, look at the table. So that's going to have 5 electrons in its outer shell. So let's draw that. So we've got nitrogen here. We're going to have 1, 2, 3, 4, 5. Okay, and then that bonds with 3 hydrogens. I wonder where they're going to go, everyone. Wonder where they're going to go. They're going to go with these ones. So that's going to go there. That's going to go there. That's going to go there. Hydrogen, 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 electron, electron, electron. Each one from the hydrogen. And there we are. Easy peasy. On to the next one. Part B, the table shows the names and formulae of some ammonium compounds. Okay, adokie then. Name and formula. Right, so we've got ammonium sulfate, that's been done for us. We have to fill in the table, that's part I. So this one, we can kind of follow a trend here. That's ammonium sulfate. This is the sulfur ion. This is the chloride ion. So I wonder if it's going to be ammonium chloride. And it is. Ammonium chloride. Okay, then we need to do ammonium carbonate. And a carbonate is CO3 minus. A list of ones that you need to learn. So I'll write them out for you so you know them. So we've got hydroxide, that's OH minus. Then nitrate, which is NO3 minus. Then sulfate, SO4 minus. Or there's also carbonate, which is the one we've used in this question. Uh-oh, my face cam's in the way. There, we actually got there for now. And then we also have phosphate. We have all 3 minus. Not as common, but still quite handy to know. And then we have ammonium, which is the one that's positive that you have to learn. So ammonium is NH4 plus, which is kind of the titular ion in this question. Ammonium. So these are just a group of ones that you need to learn. They're called the polyatomic ions, and there they all are. So I would put them on a flashcard. That would be quite beneficial. They come quite a lot. And there we are. So carbonate, CO3 minus, ammonium's NH4 plus. Therefore, we're going to need 2 of them, much like this sulfate needed 2 of them here, because sulfate and carbonate have the same charge. So it's going to look pretty similar. So we're going to have then NH4 and then CO3. And that is ammonium carbonate. There we are. In part 2, when ammonia reacts with sulfuric acid, ammonium sulfate is formed. write a chemical equation for this reaction. We're being told what ammonium sulfate was in the last question, which is quite nice of them. So all we need to do is just fill it out. So we've got ammonia, which is NH3, plus sulfuric acid, which is H2SO4. That's going to go to ammonium sulfate, which we were told in the last question was NH4 2SO4. So then how are we going to balance this? So we're going to need 2 ammonias. That's a big 2, and that's going to be 2 of those. And how many hydrogens do we have? Well, we have 8 here. Then we have 6 here, 7, 8. It's pretty good. And then sulfate and sulfate. Happy days, that's that. Grand. And then describe a test for ammonium ions. Okay, okie then. So I want to make ammonia gas, which means I want my ammonia back. What I'm going to do is add an alkali, so add sodium hydroxide. So if I add that, that's going to give me my ammonia back, essentially, and like the gas form, which then means I can use litmus paper, or I can use a metal indicator paper, technically. Actually, no, I can't. I'm going to use litmus paper, either red or blue, either or. I'm going to use red. So use red litmus paper to test the gas coming off. That's where it's coming off from this reaction that you just added this into. And then red litmus paper will turn purple, or will turn blue-ish, because, not purple, blue, because it's blue, because ammonia is an alkali. Therefore, it's going to go blue. And that's what litmus paper does. So remember, red either goes blue in alkali or stays red with acids or with neutral solutions of neutral gases, neutral compounds, whatever they mix it with. And then blue litmus paper will either stay blue with an alkali or something that is neutral, or it will turn red with an acid, kind of does the opposite. And then if it's neutral, it doesn't do either, just kind of stays the same for both of them. So red litmus paper will turn blue. So you could have used blue here and then say it will stay blue. That's fine. Will turn blue. But for a test, I like to have like an actual colour change that I can see, but it doesn't really matter at the end of the day. And there we go. That's going to be 3 marks. On we go. Part C. This table gives some information about ammonia and ammonium compounds. Calculate the percentage of nitrogen in ammonium nitrate. Okie dokie then. To find the percentage, we need to find the fraction first. So we're going to find the MR of how much nitrogen there is in there. So like the MR of nitrogen, divide that by the total MR, which you'll find like the fraction of nitrogen in this compound, and times it by 100 to find the percentage. So if we then fill out those numbers, so the MR of nitrogen, we've got 2 of them, right? And nitrogen is 14, look at the periodic table, therefore we're going to have 28 on top, divided by the total MR, which was 80, and times that by 100, and you get 35%. And that is your answer. On we go. Part 2 then, the last part. Fertilizers add nitrogen to the soil to help plants grow. Ammonia and ammonium sulfate can be used as fertilizer. Discuss the advantages and disadvantages of using each of these compounds as fertilizer. Read information on the table in your answer. The pH of rainwater is about 5.6. Okie dokie. So we're comparing ammonia and ammonium sulfate. So what's the difference between these two? Well, they're very different, and they're very different. So let's compare this. Do the percentage of nitrogen first. So ammonia having a higher percentage is better because what they're aiming for is a nitrogen, right? All the other ions are kind of irrelevant in this. We've been told that fertilizers add nitrogen because plants like nitrogen. Therefore, the one with a high percentage of nitrogen will be, in theory, the better one for this purpose, right? Let's put that down then. Okie dokie, so that's that. And then what else can we say? Let's say about the pH. So we've been told that ammonia has a pH of 11, which is very high, isn't it? Much higher than what it normally be for things like normal soil or rain or anything like that. That's what we're told. And then ammonium sulfate is a pH very similar to rain, only off by 0.1, right? So ammonium sulfate shouldn't change the pH of the natural soil because the rain is the rain, right? And that's going to kind of determine the pH of the soil. That's that's going to affect the soil most often. Whereas this guy, pH 11, massive, right? And it's too high a pH. We can assume, obviously we don't really know, we're not gardeners, are we? We're GCSE students, or IGCSE students in this case. We're not gardeners, but we can assume that plants aren't maybe going to like high pH. Maybe, hopefully, fingers crossed, we can assume that. So, as that's kind of like a very obvious possibly disadvantages. We're kind of told, if we weren't told this, we're kind of a bit more clueless, but we can assume they don't like that. So let's put that down. And the next thing, a slightly harder point, is to do with the states of these. So ammonia is a gas, whereas ammonium sulfate is a solid, right? So a gas, obviously, where the plants get ions from is through the roots in the soil, right? So a gas is no use to a plant. Therefore, you're going to have to dissolve it in water first to turn it into a solution that the plants can actually, use. And whereas this one is already a solution. If you put that into soil, it's going to dissolve, right? Into the water that it's mixed with, that's going to be in the soil. So much easier for the plant to be able to digest and use and make new things with, right? That's something else to say. Let's put that down. So yeah, so then NH3, so the ammonia has to be dissolved in water first, so it's harder for the plant to use. There we go, that'll be 4 marks, and that is the end of the paper. There we are, and that was the paper. So let me know how you all found it. If you have any questions, any comments, concerns, feel free to leave them down below. I try and respond to everyone within reason. If it's something that's like respondable, right? I try and respond to everyone, so feel free to ask any questions you might have. If you have any paper requests, then feel free to leave those as well. But yeah, so hope you all enjoyed. I hope it's been helpful. And I shall see you all in the next one. So I'll see you then. Bye!